Welcome to InterSpeech 2020. I am Abhijit Singh from Spire Lab Electrical Engineering Department, Indian Institute of Sciences, Bangalore, India. And I'll be presenting my paper titled Attention and Encoder-Decoder Based Models for Transforming Articulatory Movements at Different Speaking Rates. This is the outline of my presentation. First, we'll have the introduction, followed by the data collection process. Then we'll talk about ASNet, the proposed model, and the experimental setup. And at the end, we'll go through the results. Now, I'll briefly talk about speaking rate and its effects on articulatory motion and motivation for this work. Speaking rate, as we know, is simply how fast or slow an individual is speaking, and it can be objectively defined as a number of phonemes spoken per second. Speaking rate has a direct impact on the articulation and thus many acoustic properties like vowel duration, vowel form and frequencies, consonant-vowel co-articulation, average syllable duration, and pronunciation. And the variation in these acoustic features due to change in speaking rate impacts the performance of many speech applications, for example, ASRs. The primary motive for this work is to make these speech-based systems robust to variations in speaking rate by understanding the nature of articulatory dynamics at varied speaking rates. Preliminary work has been done on this topic, where variations in the range of articulatory moments are modeled using various transformation methods like an affine transformation, with both diagonal and full matrix, and a nonlinear transformation modeled by a deep neural network. As all these transformation methods work at the frame level, which require dynamic time warping (DTW) to time align articulatory moments at different speaking rates. The main limitation of this work is that it only models the variations in the range of articulatory moments, but not the duration variations across the varied speaking rates. All these limitations are taken care of by our proposed approach. In this study, we consider the best numbers from this work as our baseline. Transforming articulatory moments from neutral to either slow or fast speaking rate is the primary objective of this work. And to do so, we propose an encoder-decoder based attention network named ASNet. We also analyze how ASNet is able to perform phoneme level duration transformations and their amplitude scaling while going from neutral to different speaking rates. Let's take a look at the data collected for this work. The stimuli for the dataset comprises 460 phonetically balanced English sentences from Mocha-Temmet corpus. 5 subjects, 3 male and 2 female, took part in the data collection process. On the right, we have an image of EMA AG501 used to record articulatory movements. And in sync, speech was recorded from these subjects using a T-Bone EM9600 shotgun. The phonetic transcriptions used in the analysis study are obtained from Sonic Speech Recognizer, which has a 55 phoneme set, but 5 phonemes didn't appear in the force alignment process, thus making it a 50 phoneme set study in our case. To record articulatory movements of a person, we attach 9 sensors, and the positioning of the sensors is shown in the diagram. Here, we have a few samples of articulatory movements of upper lip and lower lip recorded at fast, neutral, and slow speaking rates. We observe that as we grow from faster to slower speaking rates, articulators tend to have an increased range of movements, and the durations of these movements are also longer. As we can see in this figure, we have an utterance. This was easy for us, and 2 articulators, upper lip and lower lip, for all 3 speaking rates, fast, neutral, and slow. As we go from slow to faster speaking rate, we can see the articulatory movements are much smoother and their durations are also shorter. Now, we'll discuss the architecture of the proposed network, ASNet. Articulatory movement speaking rate transformation network, or what we call ASNet, captures duration information to transform articulatory movements from neutral to varied speaking rates. As shown in the diagram, ASNet's 3 major components are encoder, decoder, and attention. Encoder is a single bidirectional LSTM layer with 512 units, and it takes articulatory moments at neutral speaking rate as input. Whereas decoder comprises two unidirectional LSTM layers with the 1024 units, followed by linear projection to predict articulatory moments at either slow or fast speaking rate. In between encoder and decoder sits a location-sensitive attention network which performs duration modeling between articulatory moments at neutral and target speaking rate. Now, getting to the experimental setup. We have a four-fold setup with 3:1 dataset split into training and testing. As attention networks require lots of training data in order to learn optimal alignments, and due to the scarcity of training data, we adopt generic and subject-specific fine-tuning on top. In this study, we have used dynamic time warping or DTW distance between predicted and original articulatory moments at target speaking rate as an evaluation metric, as the same metric is used in the baseline study. In this study, we perform three types of training with ASNet. In subject-dependent training, we train a total of 5 models, 1 model per subject with random initialization. In case of generic training, only 1 model is trained for all subjects with random initialization. And on top of this generic trained model, we fine-tune it with each subject's data. Now, we'll go through the results. Here we have neutral, original, and predicted articulatory moments of upper lip, lower lip, and right commissure for both neutral to fast and neutral to slow transformations. All the shown articulatory moments correspond to the utterance "this was easy for us," spoken at fast, neutral, and slow speaking rates. In this figure, we can observe that durations for almost all cases are predicted accurately, and the trend of the predicted articulators is similar to that of original ones with slight misalignment. In this table, we have average DTW distances for baseline and trained ASNet models for each subject. The first model is an identity transformation using DTW alignment from neutral to varied rate. Then we have the best numbers from the baseline. After that, we have 3 ASNet models trained according to the methods discussed previously. This table refers to articulatory transformation from neutral to fast speaking rate. We observe that the fine-tuned ASNet has the best performance with lowest DTW distances for each subject and outperforms the baseline. And as for ASNet generic and subject dependent, generic DTW distances are slightly higher than the baseline, and subject dependent performs worst of all ASNet models. Same trend is also followed in case of neutral to slow speaking rate articulatory transformation, with ASNet fine-tuned model outperforming the baseline. In both cases, ASNet subject-dependent models have lowest performance, and it's due to the lack of subject-dependent training data. Whereas ASNet generic models show improvements over subject-dependent and identity transformation models. And ASNet fine-tuned models have the best numbers, as these models have already learned all the generic transformations from multiple speakers and also the subject-specific transformations. Relative percentage improvements of ASNet fine-tuned over baseline for neutral to fast transformation are 2.09, 1.79, 2.75, 4.32, and 2.8 for each subject respectively, and 5.74, 7.33, 3.17, 6.36, and 10.33 for neutral to slow transformation. Not only is ASNet better than the baseline in predicting articulatory movements at target speaking rate, it also predicts the duration of the articulatory movement trajectory, thus eliminating the need to align the articulatory data of both speaking rates prior to training. Before going to the analysis study, let's discuss what is standard deviation of articulatory trajectories, or SDAT. It's used to measure the span of articulatory movements. As we know, some articulators like tongue tip, tongue body, and tongue dorsum have much larger range of moments as compared to others. And these articulators have higher SDAT values indicating the same. And we can also see in the figure that articulatory moments with larger range have larger SDAT values. As we go from faster to slower speaking rate, range of movements increases and so does respective SDAT values. And this is confirmed by this statistical study referred at the bottom, in which SDAT for each articulatory trajectory is calculated for 3 speaking rates for 5 subjects. We can observe that movements at slower rate have larger SDAT values, which is indicated by the bar height in this figure. Now, coming down to the analysis of predicted articulatory movements by ASNet. Here we verify that ASNet does learn to scale at the amplitudes of predicted articulatory movements by using standard deviation of articulatory trajectories, SDAT. In this figure, we have a box plot of SDATs of neutral, original fast or slow, and predicted fast or slow articulatory moments for all articulators. In this figure, we can see that for all articulators, SDAT values for original and predicted articulatory moments are similar in both neutral to fast and neutral to slow transformation cases, validating that ASNet is able to learn amplitude scaling. In this figure, we have a box plot of phoneme durations from all the utterances for neutral, original fast or slow, and predicted fast or slow articulatory moments. We observe that neutral durations are longer than predicted fast and are shorter in case of neutral to slow. And a similarity between original and transform articulatory trajectories can also be observed from this figure in both neutral to slow and neutral to fast cases. We perform a pair t-test between original and predicted duration to verify that ASNet transforms the duration at phoneme level, as 7 phonemes in case of neutral to fast and only 1 phoneme in case of neutral to slow came out to be significantly different. To conclude, ASNet learns transformation of articulatory moments at different speaking rates and outperforms the baseline. Time alignment of trajectories is eliminated and ASNet predicts the duration of the resulting trajectory. ASNet is able to transform articulatory moments at phoneme level and also performs amplitude scaling. Currently, we have 2 fixed rate transformations, neutral to fast and neutral to slow, and we would try to incorporate a parameter which controls target speaking rate at which articulated moments will be estimated. And we would like to eliminate the need of training separate models for fast and slow transformations by conditioning the training process and training a single model for both cases. At last, we thank all subjects for their participation, and we also appreciate the support of DST and Government of India. That will be all from my side. For any questions or suggestions, please write to us at spirelab.ee@isc.ac.in.